Then we have to calculate XL. We are given 1.4 millihenries, and therefore XL is 2 pi FL times the length. That gave us 87 man, 0.98 ohms. Then the impedance will be 0.2 ohms per kilometer, so it's 0.2 times 400 plus XL gives us a value of 96.65 at an angle 65.6. Then Y is G plus 2 pi FC times L again. That gives us 565.56 times 10 to the minus 6 angle 90. G is the conductance, and that's normally 0. So gamma L is the square root of YZ. That gives us 233.8 times 10 minus 3 at an angle of 78 degrees. ZC, square root of Z over Y, which is 413.392 angle minus 12. Then cos gamma L, you can calculate that, but it is 0.975 angle 0.658. Sin gamma L is 0.232 angle 78. Then we have to calculate Vs, which is VR cos gamma L plus IR ZC shin gamma L. If we substitute everything in there, then we get 113 kilovolt at an angle of 10.8 degrees. Sending in current IR cos gamma L plus VR over ZC shin gamma L. And that gives us a value of 402.539 at the angle of 31.3. Then I wanted to calculate the power received, and we have A is 0.975 at an angle 0.658. A is actually cos gamma L, and that is A, and that's alpha. That's 0.658. B is ZC shin gamma, and that is B angle beta. So it's 95.907 angle 65.8. Now we just substitute in the formula. Vs over VR times VR divided by beta cos beta minus delta minus A VR squared over B cos beta minus alpha. So now we've got all the values. We can just stick it in. That's beta, that's delta, which is always the angle of the voltage. And alpha is cos alpha's angle. And that gives us 26.757 megawatt or 80.27 megawatt in total. Then the maximum value is when beta is equal to delta. And we do the same calculation and we find that it's 194.38. That is the theoretical maximum power that can be transmitted by the line. Now all these problems basically form is the same. You've got your recipe, just follow it. Now if we look at question 2, same thing happens. It says there the sending end current, we must determine that it's 100 megawatt and the voltage is 278 kilovolts, power factor 0.707 lagging. That gives us a current of 293.71 at an angle minus 35. XL 2 pi FL 314 times 1.35, 10 minus 3 times 23 of 220 gives us 93.317 ohm. Then Z is 0.2 times 220 plus 93.317, which is 103.17 angle 64.8. Y is G plus 2 pi FCL gives us a value of 691.24 times 10 minus 6 angle 90. Comma L, square root of YZ, which is 0.267 angle 77,4. ZC is the square root of Z over Y. That gives us 386.4 angle minus 12.6. Cos gamma L is 0.969 angle 0.86. And shin gamma L is 0.264 angle 77. Then we can calculate VR, V cos gamma L minus ISZC shin gamma L. That comes to 127.622 kilovolt, angle 3.6. IR is IS cos gamma L minus VS over ZC shin gamma L. Gives us a value of 369.497 angle 56.4 negative. Now, the rise in voltage is the voltage when the load is thrown off. That is V divided by cos gamma L. And the voltage regulation is that voltage minus the line voltage divided by the line voltage. That gives us 278, and that's 3.3%. Again, if we calculate the receiving power, Vs times Vr over beta cos beta minus alpha, minus delta, minus AVR squared over B cos beta minus alpha. We substitute the values. That's the angle of Z, that's the angle of voltage, impedance angle, and the angle of A, which is cos gamma L. So if you put that in there, 0.86, you get 28.769 megawatt per phase, or 86.306 megawatt. And the maximum again is when beta minus delta is equal, beta is equal to delta. And then it becomes 132.838 megawatt per phase. All right, this is not megawatt, this is watts now. And that gives us 398.514 megawatt. And that's basically how all these problems work. Now, if you want to draw the phasor diagram, let me just get this book out. There's the universal power circle diagram. So you start off at a point here, N, which references will be given there, and P is there, reactive power, and that is your active power. And your angles, you start off with beta as your reference line, and then beta minus delta is this voltage line here, Vs times Vr over V squared, and this line here is AVR squared over V squared at that angle there. So that's where you get your angles from. That is your fire receiving end power factor, and that should be ISV. So that gives you the true power. That is your radius part there from N to P. So do you think you will be able to draw it? In a test, you just have to show me this. It will be fine. So you can just check and make sure that you know what values these are. Put it in. That's your angles, theta, beta minus delta. And that angle is delta. Any questions? You see, now they've made a modified universal power factor where they just moved everything to the origin. But this one is fine. All right, any other questions? Yes, Tavi. Chavi, you've got a question? You raised
Sorry,
your
I
hand.
have now I was struggling to mute to unmute. Good evening, sir.
What?
Now tell me I was struggling to unmute.
I'm trying to agree.
Struggling to unmute so I can able to talk.
Whoa, okay. But you got it.
The your angles, must it be 100% according to scale
No,
or?
just more or less.
Okay, no,
If you
thanks.
draw something like this, it's fine.
All right,
Just
thank you.
indicate the values there.
Okay.
That's basically all.
All right.
Okay, great. Then, if you go on further, I don't know if this book has got this in, but the next one will be the power flow. Okay, I'll just go and fetch my other book. See this one, I think it is. And that's the book's name. Oh, let me just get the book. I've done some examples in that notes that I gave you. So just have a look at them. Okay. Let's look at this example here. It says there, this figure is 6.9, one line diagram with a simple 3-bus system. The generation at bus 1. Magnitude of the voltage is adjusted to 1,05 per unit. And the scheduled loads at bus 2 and 3 are marked as in the diagram. Right, the line impedances are marked in per unit on a 100 MVA base, and the line charging susceptances are neglected. So the impedance between 1 and 2 is 0.02 plus j 0.04, and so on. Now let's use Gauss-Seidel, which is the one that we're actually going to look at. So y12 is the inverse of, let me just handle this. Right, and then you get 10 minus 20. Similarly, y13 is 1 over 0.01 plus 0.03. That gives us 10 minus j30, and the inverse of 0.0125 plus j 0.025 is 16 minus j32. Right, so now the admittances are marked. Now we must find the P at the P and the Q buses. The complex loads expressed in per unit, because it's all on a base of 100 MVA, is 256.6 plus J102 divided by 100, and it's negative. So it's minus 2.566 minus J102. And then it plus 3 is 138 plus J45.2, again negative. And that means scheduled AVA at the bus there is minus 1.386 plus or minus J,052. Now, V21 is Q scheduled minus JQ scheduled over V2's conjugate plus Y12 V1 plus Y23 V3 naught plus Y12 divided by Y12 plus Y23. Now, then you can calculate it. Stick your values in there, minus 2556, and then change that sign because it says minus. And 1 plus J naught plus 10 plus J20, that's the voltage at the one bus, plus 16 minus 32 at 1 plus J naught. There you can see again, that is 1,05. That's V1, Y1, 2. All right. And then you get 0.9825 minus J0.3. Now, V31, again is P3 scheduled minus JQ3 scheduled divided by V3's complement, conjugate, plus Y13 V1 plus Y23 V21. You see now there's your new V21 that you used. So this is iterative method. So the answer that you get there, you're going to use in the next one. So that'll be minus 1.386 plus J.452 divided by 1 minus J naught plus 10 minus J30, 10 plus 1,5 plus J0, Y13 V1. And then Y23 V21, which is that value that you use there, you put in the formula again, divide by Y13 plus Y23. Now for the second iteration, we have V22. Again, that is the voltage there. And then you used V1, that value, plus 10 minus J20, which is Y12 V1, plus 16 is Y23 V3 divided by 122, Y22, sorry. So that's the value there, V31 that you get. You're using V22. And then V32, you're going to use the values again. That voltage there is V31, 10 minus J30, 1.05, plus 16. And again, that will be V22, which is the one that got calculated there. So that's the process. Now, normally when we write a test or so, I'll just ask you to calculate up to here. Because now you can carry on with these iterations until the solution is converged with the accuracy of 5 times 10 minus 5. That means the fifth decimal then will remain the same. So there you can see it remained the same there. Number 7, the same as that one. And then you can determine V2 and V3. And then you can determine the current flowing between the two buses and all the buses. And then you can determine the power flow, which is way above what we are going to do. So you must just make sure that you understand these formulas, which is V21 that you calculate with V2 naught, which is given there, Y12 V1, Y23 V3. So if you look at V2, that's where you calculate. So that will be the scheduled power divided by the voltage of that bus plus Y12 times that voltage plus Y23, 23 is that part, times V3 naught. That's your first step. And you divide by Y12 and Y23. The second step, again, that will be V31 is P3 scheduled over V3 conjugate plus 13 times V1 plus Y23 V2 divided by 13 plus Y23. And
Jose,
then,
can you lower the page? We couldn't see.
sorry. All right, there it is. So V3, so that's what your first iteration is to determine V2 and V3. Once you are done, then you start with the second iteration, which is V22, and then you use V2's new value there, plus 10 minus 20, Y12, times that voltage, plus 16 minus that one, times that voltage, which is the new one, V3, divided by 13 plus 23. And the same for the third one. Then you use the values of the second V31, and again, that will be V2, the new value of V2. Where is that now? This one. So that's how the iteration is going to work. I've given you the 2 examples or 3 examples that's in this book here. So if you make sure that you can do them, I think you will be fine in the test. Because that's basically what I can ask. And then the last one is for economic dispatch. We're just going in the book, the first if you look at that examples that I gave you, book is going into too deep. Now, okay, let's see. Get hold of my book. I wonder if I got all 13 of them. I think I'm too fast here now for the book. 12. All right, there we have economic operation of systems. Okay, the first thing that we're going to look at is the distribution of load between units within a plant. So to determine the economic distribution of load between the various generating units, the variable operating cost of the unit must be expressed in terms of the power output. Fuel cost is a principal factor in fossil fuel plants, and cost of nuclear fuel can also be expressed as a function of output. All right, so now they gave us a power output in megawatt and the fuel input. And then, right, if we express the ordinates of the input-output curve in dollars per hours and let Fi be the input to unit I, dollars per hour, and PGI is the output of unit 1 in megawatts. The incremental fuel cost of the unit in dollars per megawatt is dPGI, whereas the average fuel cost is the same unit as Fi over PGI. So if the input curve of the unit I is quadratic, we can have Fa is A1 over 2 PG squared plus Bi PG plus Ci.
Can you,
Yeah.
Mr. Law?
Oh, yeah,
Can you
I haven't
please
shared the screen. Sorry. Let me just see if I can get that. Share screen. No, basic. Okay. So there we say, hence the input output curve of unit I is quadratic. We can say its Fi is Ai squared, Ai over P2 PGI squared plus B PGI plus Ci. Now, the incremental fuel cost denoted by lambda, which is defined as dF over dPGI, which is A PGI plus B, where A, B, and C are constants. Okay, so here we can see they give us some values there. And let's look at an example. For a plant with 2 units operating under economic load distribution, lambda of the plant equals lambda I of each unit. So lambda is dFi over dPg1, which is AI Pg1 plus B1. Lambda is dF2 over dPg2, which gives us A2 Pg2 plus B2. So if we solve for Pg1 and Pg2, we get Pg1 is lambda minus B1 over A1, and Pg2 is lambda minus B2 over A2. Okay. Now let's look at an example. It's much easier. They say incremental fuel cost in dollars per megawatt hour for a plant consisting of 2 units is lambda 1 is 0.008 PGI plus 8. Lambda 2 is 0.0096 PG2 plus 6.4. Now, at light loads, unit 1 will have higher incremental fuel cost, and it's operating of a lower limit of 100 megawatt, for which DFPG is $8.8 per megawatt. When unit 2 is also 100, that gives us 7.36 megawatt. Therefore, as plant output increases, the additional load should come from unit 2 until df2 dpg equals 8.8. So we can say that 0.0096 pg2 plus 6.4 is 8.8, and pg2 is then 250 megawatt. And the total plant output is 350 megawatt. So from this point on, the required output of each unit for economical load distribution is found by assuming various value for PG total, calculating the corresponding plant. So now we're going to say, all right, for 250, we get 784. For unit 4 is 100 and 150 megawatt. 350 is 8.8, and 100 and 250. That gives us 350. 500 is 9.45, and that gives us PG is 182 and 318. So for each value, you're going to substitute it in this equation of yours to get to those values. All right, so if we wish to know the distribution of load between the units for a plant output of 500 megawatt, you're going to say PG total is PG1 plus PG2, which is 500 megawatt. Now, alpha total is 1 over alpha 1 plus 1 over alpha 2, the inverse of that. So that's 0.008 plus 0.0096. The inverse of that gives us 4.3636, 10 minus 3. B total is A total B1 over A1 plus B2 over A2. So it's 8 total, 8 over 0.008 plus 6.4 divided by 0.009.